Okay, so let's continue with the next talk with our fellow KCD organizer from Provence, Donia, from Isovalent slash Cisco right now. And the topic will be what happens when eBPF meets the GPU. So the stage is yours.
You. Hey everyone, can you hear me well like that? Yeah, okay, cool. Okay. Ohai Praho. Ahoy Praho. Is it right? Okay, cool. Learned that in the plane yesterday. So, hi, I'm Donia, and I'm a software engineer at Isovalent. I'm also part of the community team. At Isovalent, yes, we've been acquired by Cisco. We are doing open source products around networking and using eBPF. I'm also a KCD province organizer, and our CFP is open. So doing a little bit of promo if you want to come in the south of France in December, and it's sunny, I promise you. So we're going to talk today about eBPF and how eBPF is meeting the GPU and observability. So I want to do a quick GPU 101 because before preparing this talk, I just didn't know much about it, and I feel like maybe you're going to be interested to understand more what's inside. And what is eBPF for the people that are not familiar with? Where is the observability gap today? And a little landscape of what eBPF tools can offer today about GPU observability. So I would just wonder how many people are on call sometimes in this room. There are a few. That's interesting. Do you manage some GPU? Oh yeah, there is a hand. Okay, two hands. Okay, go high, guys. 3. Okay, that's cool. That's very interesting. I feel that's still very niche, but it's definitely expanding. So, do you have like dashboards today where you can see what's happening on the GPU for the 3 guys? Yeah, you have. Okay, interesting. Let's talk about it after. And it's a no over there. Okay. So this is just a very, very basic screenshot to show that we have, yeah.
These slides have changed.
Oh. Oh, your pardon. Don't worry. Thank you. So you have a very basic like screenshot of what a basic GPU dashboard can show, and it's most of the time very basic information, and we want to go deeper. So let's go into AI infrastructure stack. Don't be overwhelmed. We're going to go step by step here. So we have an application. Most of the time it's Python today. And we are running model forward and data loading in this Python application. Then it goes to ML framework. Can you see my cursor here? So I can show you. Okay. So we have an ML framework. Usually it's PyTorch, but there are a bunch of them. And then we have the GPU runtime API that computes API, and we have the driver libraries. We're going to talk more about CUDA today in NVIDIA because I got a distant access to a GPU from a friend. Thank you so much to Alex. And then we have the kernel space, and inside we have all the Cisco functions like network access, memory management, network I/O file system, all of that is running on your machine. And we have the GPU driver then that is doing the command submissions to the GPU device. The GPU device is plugged to the CPU thanks to, here I took the example of a PCI Express, but it can be other transport. And we have the GPU device that has 3 different boxes here. So the first one is the VRAM. Basically, it's storing all the gradients, all the mathematical stuff that are needing. And a KV cache, a key value cache that is going to be interesting after. We're going to talk about it. We have the compute units doing the actual compute, the core, and we have the GPU kernel exec. And here, this is the kernel for the GPU, and it's doing the math operation, all the instructions that are transformed, and some parallel execution. So yeah, doing like the main job, I guess. And I want to touch about what AI infrastructure can do because yes, we have hardware, but what can we do with it? We can do training or inference. Some buzzwords. So let's just dive a little bit what it is actually. So AI workloads are using training workflow to build a model. So you're gonna train a bunch of data. First step is to load this data. And then you're gonna go through a step called forward pass. It's just run the input model and run the input and go through the model to get predictions. And the third one is compute loss. So basically, it's gonna say, is it a dog or a cat? And it's gonna compare to the correct answer. Of course, the correct answer has been labeled by someone in the word. So I just want to raise awareness around that. Fourth, the backward pass is the calculate gradients, which tell you how to adjust the weight. Basically, it's math. We're back at the university, but definitely gradients and doing some computation. Finally, we have, not finally, sorry, but we have an SSL step, which is all reduced. Basically, if you have different GPUs, it's going to synchronize the different gradients. So at the end, you have the same answer between the different GPU. All agreed that it's a dog or it's a cat. And that's what's happening here with numbers. Finally, we have an optimization step. And now the GPU are all agreed and your model is trained and you're storing all this information that are going to be used each time you want to do inference. Because inference is about serving the predictions that we've been trained to in real time. So you're a user who is not using LLM today. Yeah, I guess everyone. So you're going to write to a prompt. Here, I say, write me a poem. Because we just don't only code. We do other stuff. And we're going to load this input in the model. And it's going to be tokenized. So in different words sometimes, like one word is a token. Then we have a prefill step. And it's going to generate the KV cache we've been talking about. So associating one word you put in the prompt to something very more, again, mathematical, to a matrix, a value. Then you're going to decode each time, like for each token in an iteration, and you're going to check in the end for all these tokens, what is the answer from the model. And at the end, the tokenize is just taking all these gradients and making it human readable for you as developer, so you understand what your prompt is telling you. So maybe you generated a bunch of tokens because you've been just talking to it like a human, so you don't care really about the words you're using. So you're going to fill your KV cache in the end really fast. So maybe we have bottlenecks here. Maybe we need to observe that kind of things and that kind of behavior. And here is just a summary of the different bottlenecks that you can observe. So on the training side, we have the computation. It can be on the communication side. You can fill up the memory with the VRAM. You can have I/O problem if you're loading too many data because your GPU is not able to handle that. And on the inference, we have, again, memory bandwidth reading the KV cache. It can be on the decode side because you can parallelize all the tokens when you are decoding them. VRAM capacity or prefill latency. So that's just a summary. It's more as a reference so you understand that it can be a bunch of bottlenecks in this workflow. And what are the tools that we have today? We are not really able to see GPU kernel execution. And on the diagram, it was all like the left box. Like the memory transfers, all of that is kind of blurry at the moment. And we are building, I guess, these tools and going through that way. But there are some vendor profilers tools like NVIDIA eCrypt, but they have a huge overhead at the moment. And you have to run a profiling session and analyze results offline, which is a bit annoying because we want to have live stuff most of the time and to see what's happening and alerts and whatever. So yeah, I like just a little bit. There is one tool that I didn't really explore, but I know it's existing. It's not based on eBPF. It's a GFX vendor from Intel, and it's like a top, and you can have some information. So as mentioned, there are a bunch of tools. All the green boxes are just tools that exist today that are not eBPF based for most of them. And on the GPU device side, we have like kind of a black box today. And I called it the visibility wall. So let's see how we can dive into this wall. And to talk about that, we're going to talk about eBPF. Who is familiar with eBPF here in this room? There are quite a few hands. Okay, please bear with me. So eBPF is like a Swiss Army knife for the Linux kernel. It lets us run custom programs inside the kernel, and these programs can observe, modify, or act on kernel events like networking, file access, tracing, without needing to modify the kernel itself. And without eBPF, if you want to make changes in the Linux kernel, you have to submit a PR to Linux Torvald, and then it has to get approved, and then it's going to take years before it's going to be in the distro. So that can be a very cumbersome process. You can also run kernel modules, but it can be very risky because of the stability. So with eBPF, that's just easier. You can run dynamically programs and load them without modifying the kernel source code itself. And it provides a safe and sandboxes environment for custom logic. You don't have actually to be afraid of running eBPF programs that are going to crash your kernel. It's not going to happen. So let's see how it works just a little bit. You have the user space and you have the Linux kernel space, the kernel space, and your app is running in the user space. Then you want to hook to an event. So the eBPF program is going to hook to trace points, kprobs from the kernel, uprobs to the user side, traffic control to see networking, or express data path, which is a component before the CPU. And it's safe because you have a verifier that is making sure that you have no infinite loops, memory safety, kernel integrity, and in the end, it should be approved before going through the compiler. Then it's compiled, and the eBPF program is actually attached to your kernel. So it's interesting also for Kubernetes. I mean, we are at the KCD, so I'm going to talk a little bit of Kubernetes. So the pods are running on the user space, and the eBPF program, again, is on the host. So what's happening is that eBPF is going to have a visibility on the entire stack on all your pods with only one program. So again, that's very powerful for maintainability, for example, or debugging. So you can observe everything, and it's not limited to individual containers. And there are a bunch of tools out there like BCC for tracing, Pixie for observability, Cilium that I'm working on for Kubernetes networking. So they're all based on eBPF, and there are a bunch of SDKs with different languages. I'm a Go fan, but whatever. So let's talk about GPU and eBPF now. I want to present to you different tools that exist in the ecosystem. Note that there are most of them emerging, but there are some production-ready ones. And I want to do just a shout out to all the academic papers that have been done, because this is at the heart of what's happening in the eBPF world. So we're going to talk about runtime observability, where we can trace CUDA API, the GPU runtime library. We're going to talk about inference-aware observability when you have a LLM request, and then from the user prompt, how it goes to a final token that is generated. And about infrastructure correlation, like Casper said it this morning, like you have a lot of metrics, but how can you put a context and understand what's happening? So let's talk about the first layer. I'm going to present to you a tool called GPU Prob. It has been written by a computer science student. I would have not been able to write such a tool when I was a computer science student, to be honest. But what is it doing is that it detects things like memory leaks, kernel launch patterns at runtime, and exposes some metrics that you can then put into a Grafana dashboard. So that's very user-friendly. And then you ask your AI agent to do it as a SRE, of course. So one person asked him on Reddit, like, how it is compared to, so for example, the NVIDIA tool. And his answer is that it provides debugging and profiling live and metrics live without any overhead, because eBPF is not adding any overhead compared to tools that are using like other languages. And what is happening, it's using eBPF on the CPU side, back on that diagram. We're going to see it often. Get familiar with it. So it tells us like nothing with traditional tools about like CUDA runtime latency or more like very deep information. And here eBPF is used to probe two different aspects. So I just put a sample of this diagram to show you like, oh, you can't see. That's funny. Why it is out? Okay. So I don't know if you can see properly here, but basically it's a bunch of functions from the CUDA API library that are available in the kernel that you can just probe exactly at this point, and then you can observe them. And on the kernel itself, on the syscall, you have different functions also you can probe. For example, sched switch, and you can see when the scheduler of your CPU is switching to access to the GPU, so you can measure all the GPU access. So if it's switching too much, maybe you're gonna do some optimization on the way you're doing your tokenizing, for example, or whatever. So how does it work? GPU probe is using some different functions that are available from CUDA to see that. So we have one that is QLaunch kernel. Again, is to see each time the GPU kernel is accessed to. And the CUDA memory copy is enabling to see all the transfer data that are done between the CPU and the GPU. And then you have like output like that. If you're not familiar with eBPF, BPF trace here is just a tool to probe to Linux kernel events. And we're gonna do a little demo. Hopefully it's gonna work. Let's pray the demo god. Okay, this is so the GPU, this is a machine that I have access to, and there is a GPU running. This is an NVIDIA one. It's running Windows, which is interesting because eBPF runs mostly on Linux. So I'm running Windows for Linux. I didn't do that since a long time, but yeah. So I can do some things, but there are some things that are actually mocked up. So I can't have access, for example, to the kernel launch with eBPF. So I'm going to show you some limited function, but just wanted to show you. So here I have two programs. The first one is CUDA trace, BPF trace. And what I'm going to do is not P, but B. BPF trace on the CUDA trace.bt. And I'm attaching two props. So I'm going to attach to the memory allocation function to show you what we can do. And on this side, okay, I'm going to do a Python program that is going to run some stuff. So you can see here at the bottom, we have some function that are run and doing some allocation. And at the top, we can see the trace from eBPF. So each time there is an allocation that is done on the GPU, we can have a trace of what's happening with the PID of the function that has been called. Here's the process is Python 3. And the time, like when it was, you can also measure how long it takes. So it's just a simple, tiny thing to just show you with simple, like just simple lines of code, what we can do. So let's go back to the slide. And we're going to talk about the layer 2, about inference. And I want to present to you today eInfer, which is a tool that is correlating LLM inference with GPU activity. So what we have, again, this diagram. So we have an inference server. Can I show that? Yeah. We have an inference server here, and we have uprops at this level. So at the very beginning of the workflow, we're going to be able to trace, for example, if you're running VLM engine, the queue time of your request, how long it is taking, how much time your requests are queued. So maybe you're going to increase the number of GPU you are running. And in the world of Kubernetes, probably you're going to scale somewhere, scale out the number of GPU you have. On the GPU runtime API, we have the same function as before, memory allocation, the copy that you can have, and on the kernel side also. And on the ML framework, we have also very interesting. So do you remember like the inference workflow I showed you? So on each step, you're gonna be able to measure what's happening and observe the time it's gonna take. Again, like the memory of the KV cache, for example. So you're gonna be able to profile very deeply what's happening when you are launching a request. And how to use it? Again, that's a CLI. So it's very easy to plug into an agent AI, I guess, and just have an answer of the request for a request for the queue, the prefill, the decode step, all the stuff we've been talking about. And you can spot the bottlenecks, for example, here on the SIGINT token. I don't know what happened, like for the SIGINT batch, something was wrong. So you're going to be able to observe deeply what was happening for this one. I'm going to show you another demo just for the fun of what we can do with eBPF. So let's kill that. And okay. I'm in demo 1. Let's go to demo 2. And here I'm going to do again a sudo BPF trace on the CUDA. And here I'm tracing the memory copy between the CPU and the GPU. And on this side, I'm going to launch a Python, what's the name? GPU test 2. And what it is doing here, so again, it's a very small program, but, oh, am I launching the same thing? Oh, yeah. I was like, oh, is it the same thing? No, it's not. Oh, no, the output was good, but that's not what I wanted to show you. That's interesting. Okay. Yeah, that's the one. Okay, so here I'm allocating GPU tensors memories with different sizes. So I have a small tensor, a medium, and a large one. I'm doing some computation of matrix using matmul function for the ones who knows. And what is this interesting? So let's start here. We have the memory copy that is async between the CPU and the GPU, the hosted GPU here. And we have the allocation that we saw just before. So we are just adding more props to what we can observe. And again, this is a very sample of what we can do on all the function. I really wanted to show the like with pod and PID of pods, but with Windows for Linux, that was a mess with namespace PID. So, but you can do stuff with pods, which is interesting too. So that was the demo for the memory transfer. And I put together a remediation guide that's very high level. I will not go into details, that's more for reference, but I will share the slides, of course, but it's just to see like at each step you can have a bottleneck and how you can mitigate it today as a SRE or DevOps or an agent AI. And so to finish, I want to talk about, not to finish, I have a bunch of things to say, and I'm late. So infrastructure correlation, it's about like what you can correlate or not between all the context that you have, and as mentioned for the pods, which pod owns the GPU, which request caused the spike, and all these questions you're gonna ask yourself if you're on call, and everything is just messing up at 3 a.m. And eBPF here is just bringing on the table with these new tools correlation between what's happening on the CPU, on the processes, and what can happen really on the GPU side. And this tool I wanted to present very quickly. This is EACGM. I'm not going to read everything because that's very long, but it correlates GPU metrics with infrastructure signals. And again, there is like eBPF running everywhere, like different programs hooking. And what they do in the end, which is interesting, I think, is that you're going to be able to correlate all the layers that we just show here. This is from their GitHub, so you know. All these layers into something that is understandable as a mathematical or data analyst human, probably. But just to understand multi-layers information and metrics about what's happening on your GPU side. How do you use it? Again, that's a CLI tool, which is very powerful. Again, because you can just run it in any workflow as the DevOps. Some remediation guy, like what are you doing if you have too many CUDA memory copy, as we saw. You can reduce the memory copies, you can tune that, for example. And what about the feature vision? So as mentioned, there are a lot of research going on. If you go to Linux Plumber conference, you're gonna see that there are a lot of topics these last 2 years, actually. And there is eGPU tool that is actually injecting metrics and programs inside the GPU device. So we are breaking this visibility wall layer today through to that. And it's using PTX injection, which is GPU assembly language that is intermediate from NVIDIA. So you're going to be able to instrument directly into the GPU using that kind of tool. And they're actually working on expanding to other GPUs, not only NVIDIA's one. Yeah, it's in research stage. So the usage, again, it's a CLI, so very powerful. And you can have like different level of bottlenecks again in the GPU device side. And for different operation, you have different solution, of course. But again, that's for reference. So you can read that later. The other one I wanted to present is agent side. So I've been talking here about GPU, but and very hardware side, I feel. But we are going more and more around what agent can do for us. I tend to say that we are going to be AI agent managers and not developers anymore. And how can we observe what they're doing is also important. So agent side is one of the tools doing that. Anyway, I wanted to thank you. And so the main key takeaways today is that GPUs are infrastructure now. It's really part of the global infrastructure. Not a lot of people raise their hands today about GPU, but I feel like if I ask this question next year, we're going to have much more hands. So it's going to be interesting. eBPF observes the boundaries. So we saw the CUDA runtimes, the kernel transition, and all the things that eBPF is able to hook on. And correlation matters more than metrics. I think that's the theme today. Like, how do you have this how do you make these metrics making sense to people? And again, the ecosystem is very early, but I feel that's very interesting to see what's happening. Very exciting. I can't wait to see more and more contributions to it. And if you want to shape the ecosystem or curious about it, I feel that's a great time to be in the first time player. I'm also part of the Merge for an initiative, and I would love to see you in the Slack channel if you're interested in. This is a diversity initiative from the CNCF, and we are running events at KubeCon, some programs. So you're more than welcome. Thank you so much. Feedback is a gift, I tend to think. So if you want to give feedback about my talk, I would love to. This is my first time like doing it, so I would love to see what you think about it. And I put all the resources of the different academic papers and blog posts that I've been using to build this talk. So thank you to all the community of the open source for that. And if you're curious about eBPF, there is a lab from Isovalent company. I love the fact that you don't have to install anything on your laptop and can just go somewhere and just get your hands dirty. So thank you. That's a very good question. I think that at the moment, you can't, but I feel that the gap to do it is not big, I think. That's just about formatting. Will Cilium default metrics got this someday? That's a very good question. I hope so. I think that I didn't talk about network here. I talk more about like the GPU aspects, but definitely in inference, especially, we want to spot where are the network like spikes, where are the network latencies. So it should be. I guess it depends on the clients. Is it compatible with NVLink? Yeah, it is. Okay, it depends on the tools. that you're using, but there are some tools that are compatible with NVLink transport. Will the slides be available somewhere? Definitely. I usually put my slides on speaker deck, but I will share them on my LinkedIn. So I would love to connect. My name is Donia. Is eBPF secure? Yeah, so that's why I mentioned that is eBPF safe? You can't crash your kernel. Like all the things you can do is write programs that are hooks to what's happening and different functions. And you can't actually hook to something if your eBPF program is not secure, because the eBPF verifier is doing his job really good. And I know some people working on it, and they're really good. Thank you so much for your questions.
Cool.